So let's suppose we have n independent and identically distributed observations chosen randomly from a population, which we denote x1 all the way up to xn. And these are drawn from a population where the expected value of the random variable x is equal to mu and the variance of the random variable is equal to sigma squared. Since the observations are drawn randomly and independently identically distributed from the population, it follows that the expectation of each of the xi's is going to be equal to the population expectation mu, and the variance of the xi is going to be equal to the variance of the population sigma squared. And since the observations are independent from each other, the covariance between observations is going to be equal to 0 for I not equal to j. Now we are presented with a slightly strange estimator mu1 hat, which is equal to n plus 1 over n squared times by the sum of the observations. Now, first of all, we might be interested in the characteristics of this estimator. So we might be interested in whether or not this estimator is unbiased or not. So remember, an estimator is unbiased if the expectation of that estimator is equal to the true population parameter that we're estimating. So in this case, if the expectation of mu1 hat is equal to mu1, that is an unbiased estimator. Intuitively, that means that if we repeatedly sampled from the population, if we used this estimator on repeated samples, if it's an unbiased estimator, on average, this would give the true population value mu. So let's start by taking our expectations of our estimator. So the expectation of mu1 hat is going to be equal to the expectation of our estimator, which is n plus 1 over n squared, times by the sum of the xi's. Now, there are various rules that we can use with expectations, and remember, the expectation of any constant multiplied by a random variable, so for instance, if a is a constant and x is a random variable, this is equal to that constant a times by the expectation of x. So we can rewrite this as being equal to, we can take the n plus 1 over n squared outside and rewrite this as being equal to n plus 1 over n squared times by the expectation of the sum of the xi's. And we also know that the expectation of a sum of random variables is equal to the sum of the expectations. So we can take this expectation inside the summation. So this is just going to be equal to n plus 1 over n squared times by the sum of the expectations of the xi's. Now we know that from our assumptions that the observations are IID, that the expectation of each of those xi's is always equal to mu, so we can replace each of these by a mu, so that's going to be mu plus mu plus mu plus mu n times, or n lots of mu, so we can rewrite this as being n plus 1 over n squared times by n lots of mu, which is equal to n plus 1 over n times by mu. Now, the bias is just defined as the difference between the expectation or the average of our estimator, so the expectation of the mu1 hat, minus the true population parameter that we're estimating. We know that the expectation of our estimator is equal to n plus 1 over n times by mu, so we can write down this as being equal to n plus 1 over n times by mu minus mu. If we put everything over a common factor of n, this will be equal to n plus 1 times by mu minus n lots of mu all over n, which is equal to, we have n mu minus n mu, so those cancel, just leaving us with this is equal to mu over n. So we've got a bias equal to mu over n because the expected value of our estimator is not equal to the true population parameter that's being estimated. On average, this estimator gives the wrong answer, and this mu over n gives you the average of that wrong answer. On average, the estimator is mu over n above the true population parameter being estimated. Now, the second characteristic we might be interested in is the variance of our estimator mu1 hat. And the variance is just going to be equal to the variance of our n plus 1 over n squared times by the sum of the xi's. So let's just substitute that into our variance in place of the mu hat. And we're going to use some rules about variances. So we know that the variance of some constant multiplied by a random variable is equal to a squared times by the variance of that random variable. So we can take this n plus 1 over n squared outside and rewrite this as being equal to n plus 1 over n squared all squared times by the variance of the sum of the xi's. We also know that the variance of a sum of random variables, so for instance the variance of x plus y, is equal to the variance of x plus the variance of y plus 2 lots of the covariance between x and y. So we can rewrite this variance of the sum of the xi's, first of all with our common factor, n plus 1 over n squared all squared. We can rewrite that variance of the sum of the xi's as being equal to the sum of the variances of xi. So that's the variance of x1 plus the variance of x2 plus the variance of x3 and so on, all the way up to the variance of xn. Plus, because we've got all the covariance terms, we need to take account of all of the cross product terms. So the covariance of x1 with x2, the covariance of x1 with x3, with x1 with x4, x2 with x3, and so on. And we can write all of those covariance terms as being equivalent to the sum from I is equal to 1 to n minus 1. And then for each of those i's, we have the sum from j is equal to I plus 1 to n of the covariances between xi and xj. And this takes account of all of those cross product terms. But because the observations are IID, these covariance terms are going to vanish, leaving us just with the sum of the variance of xi's. But again, because the observations are IID, we know that the variance of xi is a constant, which is equal to the variance of x. So we can rewrite this as being equal to n plus 1 over n squared squared times by the sum of sigma squared. But we've just got n lots of sigma squared here, so this is going to be equal to n plus 1 squared over n to the 4 times by n lots of the variance of x, which is sigma squared. And then we can simplify this a little bit to give us n plus 1 squared over n cubed times by sigma squared. So far we've analysed this estimator and we've shown that on average the estimator produces an estimate different from the true population parameter mu, and the size of the bias is equal to mu over n. Now a question that we might ask is what happens to this estimator as the sample size gets very, very large? Does the estimator mu1 hat converge towards the true population parameter mu? And we can analyze that by looking at the mean square error. The mean square error provides us with a measure of the average magnitude of the error of the estimator. And it's defined as the square of the bias plus the variance. Now, an estimator can be said to be consistent if the limit as n tends towards infinity of the mean square error is equal to 0. So in other words, as the sample size gets very, very large, if the average error of the estimator tends towards 0, then our estimator is consistent. So in this case, we can write our mean square error as being equal to the bias squared. The bias was mu over n, so our bias squared is going to be mu squared over n squared, plus the variance, which is n plus 1 squared over n cubed times by sigma squared. So let's examine what happens to our mean square error as the sample size tends towards infinity. So we're taking the limit as n tends towards infinity of our mean square error, which is the same as the limit as n tends towards infinity of mu squared over n squared plus n plus 1 squared over n cubed times by sigma squared. Since we're finding the limit of a sum, we can just deal with each part in turn. And let's start by looking at the limit as n tends towards infinity of mu squared over n squared. Now this is some constant times by 1 over n squared. So if 1 over n squared tends towards 0, then mu squared, which is a constant, over n squared will also tend towards 0. So let's look at what happens if we take the limit as n tends towards infinity of 1 over n squared. But that's just trivially equal to 0 because we've got 1 divided by something that tends towards infinity. So the limit as n tends towards infinity of 1 over n squared is just 0, which means that the limit as n tends towards infinity of mu squared over n squared will also be equal to 0. Looking at the second term, let's look at the limit as n tends towards infinity of n plus 1 squared over n cubed. Now we've got something that will tend towards infinity divided by something that will tend towards infinity. So it's not immediately clear what we're going to have to do, but we're going to apply L'Hopital's rule, which says that if we've got the ratio of two functions, both of which tend towards infinity as n tends towards infinity, then the limit is the same as the limit of, as n tends towards infinity, of the derivative of the numerator over the derivative of the denominator. So the derivative of the numerator is just 2n plus 2 divided through by the derivative of the denominator, which is 3n squared. But again, both 2n plus 2 and 3n squared tend towards infinity as n tends towards infinity, which means that we use L'Hopital's rule again. We're looking for the limit as n tends towards infinity. We differentiate the numerator, giving us 2. We differentiate the denominator, giving us 6n. But now it's fairly trivial to see that this limit, we've got a constant on the top divided through by something that tends towards infinity. This is going to be equal to 0. So this also implies that since n plus 1 squared over n cubed tends towards 0 as n tends towards infinity, this whole term will tend towards 0. So the limit as n tends towards infinity of n plus 1 squared over n cubed times by sigma squared is also equal to 0. So that means that the limit as n tends towards infinity of our mean square error is going to be equal to 0 times by mu squared plus 0 times by sigma squared, which is equal to 0. So since this limit is equal to 0, the mean square error converges towards 0 as the sample size tends towards infinity. Because of this, our estimator is consistent.